Okay, so we have 2 sections left in this set of notes. Okay, this is the last of the forces. And then the last section is gonna talk about the dynamics. Okay, so tying together kinematics and forces. Okay, so again, this is one of those forces that we talked about in that table from unit 2.1. So the spring force, all right, is the force that is exerted on an object by a compressed or stretched spring. Okay, so this force pertains to elastic materials. So those materials that are allowed to return back to its original state and not be essentially be permanently deformed once it is stretched. Okay, they can be permanently deformed, right, if you stretch it too much. But again, these things are going to kind of come back to their original state. Okay, now all of these springs or elastic materials that we're going to talk about obey what is called Hooke's law. Okay, and it's a principle of physics that states that the force needed to extend or compress a spring by some distance is proportional to that distance. And so the formula, so F sub SP is going to be negative KX. And what happens is the negative sign just lets us know that this force is a restoring force. Okay, so it's going to restore back to its original position. Okay, where F is the spring force. Okay, X is the stretching or compressing distance. So stretching or compressing distance, sometimes referred to as the elongation. Okay, and then K is a special value known as the spring or force constant. Okay, you can use either term, which tells you how much force you need to exert on the spring to get it to move 1 meter. Okay, so the way to think about it is that garage door springs have high K values, while slinkies have low K values. You need to do a lot to a garage door spring to even get it to stretch a centimeter. Okay, whereas slinky, you don't have to do much, you just pull it apart. It's easy to pull apart, right? So the thing about K is just how easy or hard it is to pull that spring apart or to compress that spring. Okay, sorry, I didn't want that. Not that, I want this. Okay, so let's look at a couple examples. So how much force is needed to pull a spring with a spring constant of 20 newtons per meter, a distance of 25 centimeters? So you do need to be careful. So they give us K, okay, 20 newtons per centimeter, and then they give us a distance, right, which is our elongation of 25 centimeters. Okay, and they didn't give us K in newtons per meter. They gave us newtons per newtons. They didn't give it to us in newtons per centimeter. They gave us in newtons per meter. Okay, so you need to make sure that these units match up. So if they don't, convert your units. That's one of the big mistakes that students often make. Okay, is that they don't convert the unit. All right, and so what are we looking for? How much force did we apply? Okay, so all we're going to simply do is F equals KX. And I can drop the negative sign here if I want. The negative sign is not a big deal at this point in time. Okay, so I'm just going to do 20 times 0.25. And so it's just going to be 5 newtons, right? Now, if you say it was done by a mass, well, then we can figure out the mass of that force. So M equals F over G. So M equals 5 divided by 10, or it's like we took a ½ kilogram mass and attached it to this spring to cause all this to happen. That wasn't asked for, but that is something that they can ask you to do. Okay. All right. So the next one. So the maximum acceleration of the spring occurs when the spring is either stretched or compressed at its maximum displacement from equilibrium. If a block of mass m is attached to a spring on a table and is allowed to slide when pulled a distance of x from equilibrium, what is the maximum acceleration and force experienced by the spring when the table is A, frictionless, and B, when the table and block have a coefficient of friction between them, coefficient of friction mu between them, and the spring constant of the spring is K. Okay, so this is, where we're bringing in our forces, right? So we're going to have, again, draw, sum, solve, right? So draw this, so the drawing, right? We have Fn, we have Fg. So if we stretch it, the only force we have is our spring force. Okay. Okay. So this is part A where the table's frictionless. Okay. And so we do our draw, we do our sum. Right. So X, Y. Again, the Y direction for this scenario would be just practice. So Fn equals Fg, Fn equals mg. That's going to be more helpful in our next, in part B. And so then when we have, the only force we have is FSP, right, equals ma. And so we would do Kx equals ma, right? And so A would be Kx over m. In fact, this would be negative, 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 right? So there's the acceleration when we do not have friction. Right, so it's negative the spring force over the mass. Okay, and then here's our solve step. I know I keep forgetting to indicate the solve step. All right, so now what happens when we do the other, when we have friction now? So here's our draw step, Fn, Fg, we have FSP. Okay, the friction again is going to oppose the motion, right? And so it's sliding to the left. So that means our friction is going to go to the right. And so now we do our summing. All right, so sum of the forces in the y direction 0. And then we would have Fn minus Fg equals 0. So this tells us that the normal force is equal to the weight, which is very typical, even though it's blocked on a, on a spring. Okay, and so now we go over and do our x direction. So sum of the forces in the x direction equals ma. And so we would have positive friction, negative spring force, okay, equals ma. And so we would go through and do our we're going to solve this for acceleration. So F minus, so friction minus spring equals mass times acceleration, or over m. And now we're going to plug in to get a simplified version of this equation. All right, so friction is mu Fn, and spring force is Kx. Okay, and so we've already taken into consideration the negative sign. So when you plug in Kx here, you can just plug in the positive. Let me pan up a little bit so I'm not bending over. Right, and so friction, our normal force is mu mg, Kx over m. Okay, don't cancel the m's unless you want to rewrite this equation. So if I want to do that, it would be mu g minus Kx over m if I want to eliminate. Right, so here is my acceleration when I now have friction. Very interesting, because if you note here, when we did a sliding object, right, we found that the acceleration was negative mu g. There it is right there. And this object is sliding, right, on a surface. Now, we just happen to be that the friction ended up going in the positive direction. So that's why this mu g is no longer negative and that it is positive. All right, so one section left is dynamics. It's kind of putting it all together, which is very typical, because on a free response question, it'd be like part A, do forces, parts A and B do forces to find acceleration. Parts C and D use that number to find something in the motion side.